So welcome back to the second half of your 9th class, where I'm taking you through supervised machine learning. Before the break, I made distinction between tree-like and neuron-like, right? Method. So tree-likes are kind of like crude, sort of like logical representation of how classification problem is solved by asking a whole bunch of questions about the input, right? If the input is round shape or long shape, if it's round shape or color rate, and yes, based on your answer that you go down, you propagate down the tree. And at the bottom of the tree, you get your classification result. Okay, it's an apple, it's an orange, it's an banana. Whereas, so that's kind of like an approximation of what human logic seems to work, but it's not really how babies really identify bananas and apple and orange. So if you want to be closer to the biological inspiration, you have to look at, say, a frog's neuron, right? A frog's neuron, just take input x1, x2, x3, and multiply it and see if it's the signal is strong enough. If its signal is strong enough, then it sends a signal down the line. So this kind of neuron, which we call perceptron, can be organized into layer, and layer can be stacked. And based on that, you can get an artificial neural network, in particular, multi-layer perceptron. In this case, there'll be like a final neuron that evaluates whether or not it is an apple. There's another neuron that say whether or not it's an orange. And there's another neuron that identify whether or not it's a banana, right? And presumably, if you've done your training right, then only one neuron will light up at the end. And that neuron that lights up, if it's the apple neuron lights up, then you say it's an apple. If it's banana neuron that lights up, then it's banana. Now, of course, in real life, there'll be some ambiguous case where, you know, apples and bananas, or maybe not apples and banana, but maybe apples and orange look similar. Yeah, right. So again, the reason we have machine learning is because we can't get to the parameter value in one shot, right? This is not, again, this is, by the way, this is a Wikipedia page on linear regression. So that's got everything that we showed you before. And of course, again, right, these are, you're given the point, you find the red line, and the red line has the formula for the intercept and the slope. And that's basically this. It's sum of square xy divided by sum. So x minus x bar times y minus y bar. And then sum of that divided by x minus x bar squared. So that gives you the slope estimate. And based on that, you use, okay, so that's in one shot. Right? But we talk about machine learning. So it's like starting with beta 1 equal to 0, beta 2 equal, beta 0 equal to 0, and start moving until you get to that. Okay. Now you wouldn't do it for linear regression because you have a closed form solution. But if you have 175 billion parameter, then definitely you have to do that. So that's kind of machine learning algorithm. I try to find the original, why it's called logistic sigmoid. And, you know, even here, it's say, you know, the name is just made up. No reason why it's called logistic formula. But anyway, so that function here, this logistic sigmoid function, it's this guy. Okay. So basically 1 divided by 1 minus e to the minus x. Now, for our problem, the perceptron is exactly this, except what? Except instead of having x here, it is the w1 x1 plus w2 x2 plus w3 x3 plus w4 minus the threshold. And there's another parameter called temperature. I'm not going to tell you what it is, but it basically controls how sharp or how flat this thing is. So anyway, those are the nitty-gritty details. Now, let's say what happened when we want to work with the problem. Okay, what work with the problem? So again, okay, so this thing is think of the problem itself. Oops, sorry. Okay, oops. Right, so think of prediction as a okay. So now go to section 2, which is where I have the algorithm, right? Supervised machine learning algorithm. Now, before the break, okay, so I mentioned that the tree is the example that I show you. A naive Bayes is also a tree-like architecture, but it works slightly different. The main thing I want to mention is, of course, artificial neural network. Okay, that's the section 2.1.2. And multi-layer perceptron would be like the OG, the original gangster of ANN, right? It's the one that I grew up with. It's the one of the majority of data scientists today grew up with. And the way it works, okay, I'll send you this code, by the way. A lot of time I want you to type it myself, but this is too tedious. A lot of this is just window dressing. But what happened here is I just want to show you that. So this is one neuron, right? Now I happen to have X1 and X2 multiplied by W1, W2, right? And then this is one neuron. This is another neuron. This is another neuron. So you can imagine 1, 2, 3, combine them together, you get something like this, right? Now, this thing is not, it's then fed. This is an input to the final neuron. So in this picture here, there are 4 neurons. There's one neuron F1, one neuron F2, there's one neuron F3. Combine, this is their output, combine, multiply by the weight to the final neuron, and that's F4, okay? So I'll send you this so you can play around with, you know, trying different value, and it gets, you know, all kind of stuff, so. Right, okay? Now, I mentioned to you that once you have ANN as a class, then you have many variations. Okay, so I grew up with this thing called multi-layer perceptron. Now, this thing that you grew up with is called convolutional neural network. This is kind of, in a way, this is also, this is kind of like a theme. It's not that convolutional neural network replaced multi-layer perceptron. No, it doesn't. What it does is that it introduces a different kind of neuron function, right? Called convolutional layers, right? But once you have that convolutional layers, you still feed it to multi-layer perceptron at the end, or multi-layer perceptron-like. So like I said before, you know, multi-layer perceptron hasn't gone away. It just gets absorbed. So convolutional neural network, it's not really our subject because, you know, it's not used in, technically speaking, data analytics, unless you're talking about literally visual recognition, in which case, yeah, convolutional neural network is the key. The difference is this. If I give you like, you know, measurement of an apple, measurement of height and weight and income level, these are numerical attributes, right? Right? So you can see it's naturally X1, X2, X3, X4, right? So X1 can be weight, X2 can be income, X3 can be whatever, okay? So these are numerical input. But what if the input is a picture, right? Somehow you have to turn picture into, literally into numerical vectors, okay? How do you do that? Well, that's where convolutional layer comes from. It comes from the word called convolutional filter, which is kind of like a mathematical operation for multiplying the pixel value and detecting pattern. So I'm just going to do a hand waving because it's outside our class, it's not machine learning class. Let's say that, let's think of black and white picture, right? And there's a human stick, you know, stick figure. There's a line, there's a circle, there's a diagonal line, 45 degrees. Okay, well, if you think about it, you can't put the picture as X1, X2, X3, X4. It doesn't make sense. So before you get to X1, X2, X3, X4, wouldn't it be nice if X1, X2, X3, X4 represent something like, is there a vertical line, right? So in other words, you have some kind of visual processing, pre-processing. Is there a circle? Is there a straight line? Is there a 45-degree line? And where is that 45-degree line? You see what I mean? So you can imagine that instead of feeding some numbers, you feed in this kind of detection, this kind of filter. And that's where convolutional filter comes in, right? So it says like, hey, I detect a vertical line. I detect a 45-degree line. I detect a circle, right? And I see that there's a circle here connect to the vertical line, so it's a human stick. Now, what if you detect two circles and one vertical line in the middle and another horizontal line at the bottom? Maybe it's a face. It's an emoji face, right? So if you detect circle, circle, vertical line, flat line, so no emotion emoji. Circle, circle, flat line, parabolic curve up. That's a smiley. Circle, circle, vertical line, curve down, parabola. That's unhappy face, right? So you can imagine that if there's some kind of pre-processing that detects feature or curve or primitives of the graphics as an input, then it helps classification. Oh, is this a happy face? Is this an unhappy face? Is this a human stick figure? Is this an emoji, right? Think of that. And that's how basically in subsequent abstraction and complication, you can start to say, oh yeah, there's an eye, but there's like a whisker, so it's a cat, it's not a dog. And that's why you get this convolutional neural network. Okay, so convolutional neural network, if anybody asks, is basically a synthesis of multi-layer perceptron-like architecture with a convolutional layer. Another term I'll throw at you, but I'm not going to hold you responsible. It's called feed-forward network. That's like intermediate term. So if you have something that's feed-forward, it doesn't have to be a strict layer. It doesn't have to be perceptron. They call it feed-forward. Of course, when I say that, if you're keen, you would say, hey, wait a minute. In that case, there are some network that's not feed-forward. Yes, there are. There are network that loops back, recurrent, right? So again, let me say, I'm going to go through the work through exercise quickly, okay? But before I go that, say, anytime you have a network of artificial neuron, that's artificial neural network, okay? That artificial network just basically feeds in the signal and propagate, okay? If it feeds in one direction, it's called feed-forward network. If it feeds and come back, sometimes it's called recurrent network. So there's some, technical term. Well, multi-layer perceptron is a feed-forward because it doesn't feed back. And the neurons are of the type perceptron. And it's in layer, and there can be more than one layer. Okay, so multi-layer perceptron. Yeah. Right. Now, before the break, I did mention that sometimes you don't just have one machine learning thing. You can have some kind of different components, right? Well, imagine if I don't build one tree, but I build 5 trees and I average the output of 5 trees, right? Maybe that adds more parameter, okay? It would be like one tree can help detect vertical line, the other tree detects circle. So circle plus vertical, human face, whatever, okay? So you can have more than one tree. There are 2 classes of model that follow under that. One's called random forest and gradient boosted tree. Now, again, this is not a machine learning class, but I'm just going to give you a run through of what term you should be familiar with. If you have a decision tree, it's a decision tree model. If you have not one tree, but a whole bunch of trees, and you kind of like average the output, you sort of like assemble the output of them together. What's more than one tree? Forest, right? So random forest is a little bit like that. It's like a bunch of tree workings independently, but then you get the result and then you compile them. Gradient boosted tree is kind of different. It's a whole bunch of trees, but they kind of work in series. It's like you have one decision tree, and then you have an error of that tree, and then you have the second tree that learns to minimize the error of the first tree, and the third tree minimize the error of second tree. So it's kind of like a cascade kind of thing. Don't have to worry about that. But if you want to read, you can read all this in the, first you can go to Mathematical's reference page, and of course you can go to Wikipedia, and of course you can go to a machine learning YouTubes, okay? So these are the popular one, right? Now, ensemble neural network, you can also have that. So instead of having one neural network, you can have 2 neural networks, okay? Except 2 neural networks, sometimes they work together, sometimes they work against each other. And this is the word I want to stop a little bit. There's this thing called Siamese network. I'm not going to go into. It's a little bit. There's this thing called adversarial network. Now, this is the more interesting thing because you can have two networks. Okay, a network is a neural network trying to identify object, and then you have another network is trying to create a fake example, right? And you have a neural network that create a fake example, feed into the original network that try to identify the right example. So they compete each other. So it's like a sparring partner. So in order to have a good boxer, you have to have a good sparring partner. In order to have a fake item detector, you have to have a good faker. So you create two neural network architecture. One creates a fake to fool the first one. And the first one learns to identify the real thing from the fake thing. And they compete with each other. At the end, you use this guy. You use the one who identified the good thing, okay? Now, there's a story that's really, well, it's not story, it's real life. This is actually what deep fake is all about. Originally, okay? Now, listen to me carefully. You try to create a neural network, like convolutional neural network, that looks at picture of, say, Obama, and say, this is Obama. This is Michelle. Okay, so it's an object recognition neural network, convolutional neural network. Then you have a neural network that creates fake Obama and competes with the detect Obama detector. The idea is that if the fake neural network gets better, so does the identifier, the classifier network, right? So that's what you want to do. You want to create a classifier network that's really good at identifying Obama from Michelle, right? But of course, what happened? What gets more popular, guys, in the YouTube? The fake one, right? the fake Obama generator becomes like very popular, right? It gets viral, okay? But technically, researcher creates a fake one to make the classifier work better. Okay, but they just for fun, they just create some fake picture of Obama and then publish it and show it in YouTube or something. It gets viral. Okay, now get to your thing. Get to your. Yeah, I'm sorry, guys. I mean, I took too much of a time. Tell you what. Next week I'll run through the process. Since we don't have that much time left because we're going to go talk to the project, I'm going to go back to the screen again. Okay, I'm going to go back to the screen again and I'm going to talk validation. Okay, my apology. Okay. So this is your data. Okay. Okay, this is your data. Okay. By show of hand, which one do you think is a good model? Okay, I'm going to have three models: blue, red, and green. Okay. This is a blue model. This is a blue model. Okay. This is a red model. Okay. And this is a green model. Okay. By show of hand, who thinks blue is the best model? Good. Blue model is an example of something like regression model, right? You can only do like two coefficient. There's a slope, there's a thing, right? Okay. What's a rate model? A rate model is when you go crazy and you fit all the points. In fact, if I build a multi-layer perceptron, okay, if I build a multi-layer perceptron, roughly speaking, so this is X1. So actually, there's only one X, right? Okay, there's only one X, right? Let's say there are 30 points. Let's say there are about 30 points altogether. If I build just one layer of perceptron, but I have 30 neurons, chances are I can create the red line. It's basically the old saying, if you have n data point and you have n degree of freedom, you can fit it. Okay, so, you know, plus or minus, if I have 30 points and I have 30 neurons, I can overfit the data. The problem with overfitting the data is that it's not the real thing, right? Because you're fitting noise. You're fitting noise. So this guy underfit, this guy overfit, this guy is just about right. Picks up the trend, but not the noise. So you agree with me. Nobody disagree, right? There is such thing as overfit, underfit, and let's say optimal fit. Okay? Good. Question. First of all, if you have like statistical model, like linear regression, you can't do anything. You can only underfit. Okay? End of story. End of story. Now, when you go to a neural network, okay, if I plot you the data, maybe you can say that, well, hey guys, there's only 30 data points. So, you know, don't have 30 neurons. Maybe 2 neurons would work, but maybe 2 doesn't work. Maybe 3 works, maybe 5. What's the optimal number? The problem is you don't know. Okay, you don't know. So once again, let's go back to human beings. When you were born, you had more connections than you do now, because some connections goes away, right? So not only do the connection in your brain changes the weight, but some of them become 0, so disappear. So basically, what you should, in a sense, think about doing is having the ability to overfit, but don't overfit. Okay, let me say that again. If you don't have the ability to overfit, end of story, you don't overfit. If you have the ability to overfit, you can't immediately go to optimal fit because you don't know what optimal is. So you should think about, okay, you know what? I have capacity to overfit. How do I stop myself from overfitting? Okay, right? One strategy, as with human babies, is to start out with all the parameters in the world and then kill out some of them. Okay, that's called pruning. Pruning. Okay, so in other words, you have a whole bunch of parameters, but you have too many, so you have to prune it. That gets a little bit technical. There's another way that I'm going to teach, which is a lot simpler to conceptualize as well as implement. Okay, that's called early stopping. I'll come back later. But before I erase this picture, you agree the green is best, right? Okay. Now, in order to say the green is best, how can you say that the green is best? You say green is best is because it doesn't pick out individual data point, right? So in a way, there's some kind of like substitutability. So in other words, if you learn from one data set, or if you learn from part of it, you should kind of like get the same result. And this gets you the idea of data partitioning. Okay, what I mean is this. What I mean is, if I have 100 points, okay, if I have 100 points, okay, right? And I fit that model. And that model is good. Okay, that model is good. And then, okay, so that's good, right? That's good. Now imagine, what if I start with 100 points, but I hold out 20%, hold out 10%, just hide it, just hide 20%. And I use only 80%. It's 80%. Okay. If I use 80% and the model is good, it should do this. So imagine that the blacks is only 80%. And then I put in another, then I test, right? With another 20% of the data. Is it going to be like way down here? Shouldn't, right? It should be kind of, right? Right? Because the model is good. The model is good, right? The model is good. So, you know, whether or not you train on the whole 100 or train on, you kind of get the same model. Well, so why not do that? Why not say, hey, if the model is good, then you can use the model to fit part of the data and you get some error. And then you test against the data that the model hasn't seen, you should get similar kind of error. Does that logic work with you? Okay. So in fact, there are, okay, okay. If that black and red, does that make sense? You have a whole, your data is small, right? You don't have that many data set that did made it their point. Are you going to throw away 20%? Well, you can think of it as a testing, right? So sometimes you're not being wasteful. You're not being wasteful. So my question is, okay, my question is the model good? Okay. So if the model is good, I said the model, okay, this is a model, okay, it's tested on, let's put it this bracket, like, you know, I'm putting the bracket, okay, and the 80%, I'm going to call it training data. X training. Okay. Right. And this one is going to give you an error in training. Right. That's the dial that we try to minimize, right? Okay. So it's just like before, right? I put in the data and I keep moving until it minimizes the fitting error, right? Except now I have subscript training. Subscript training. So whether or not the model is good is I use this to train, but then I test it against testing. Right? So this is going to be a criteria. Is the model overfit? So yes, is the question. Is the model good? Okay. Now, in other words, does it overfit? Again, we're dealing with a neural network, artificial neural network, so don't have to worry about underfit. Okay, we have enough neurons. Okay, we have enough neurons. We're not going to underfit, let's say. Okay, the point is the problem is overfit. Okay, if you're dealing with linear regression, your problem is underfitting. Am I underfitting? No, in this case, you're asking, am I overfitting? Okay, so if the model is good, is the model good? Does it overfit? How would you see overfit? You would see that error in training is much less, right? 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 That's how you test. Okay, that's how you test. Okay. But testing is after the fact. The model is done. Okay, testing is done. The model is done. Okay. First of all, let me ask you this. I'm a consultant. Company pays me to analyze the data, make a prediction, and I give my result to my client. What performance number should I give to my client? The answer is this one, right? Because that one can be minimized to 0, basically, right? If I add enough neurons, I'm going to get 0, right? Because I can fit individual point, but that's not what I point, right? So I have to be honest with my client. I have to give them my testing performance, okay? Testing means, another word for it is called out of sample. Okay, out of sample. Make sense? Okay. Now, so this is whether or not it's good or does it overfit. This is not good. However, what can I do? It's already overfit. And there's nothing I can do. It's overfit, right? Well, let's be a little bit clever. Let's be a little bit clever. Let's go back to here. Okay, to here. Now, let me draw you one picture. So, if this is my, say, number of neuron, okay, or training time. Why do I say or? Why do I say or? Well, if you think about it, if I have more neurons, okay, but I don't train them, I start with 0, it's still gonna underfit, right? So basically, it's not the number of neuron, it's whether or not I allow the gradient descent to go all the way down. Okay, let me say that again. You can overfit if you have too many neurons. However, I maintain that even if you have too many neurons, you can only overfit if you keep minimizing the training error. Right? So the key parameter that pertains on whether or not you're going to overfit is not the number of neurons. In a larger scheme of things, yes. If you have a tiny model versus a large model, yes. But in practice, let's say you already download an algorithm for a neural network that has 5,000 neurons. What's going to distinguish overfitting from non-overfitting is not the number of neurons, but whether or not you allow the 5,000 neurons to minimize the error. And because by gradient descent algorithm, you start with high error, you keep going down, right? So what matters here, let's keep number of neurons out of the equation and look at the training time. Remember? So you go downhill, right? You keep go down. Okay. So this is the number of iterations. You go downhill. Okay. So what I'm going to do is, I'm going to do this. Number iteration. Okay. Right. Number of iterations. Right. Okay. So what does overfit mean? Overfit means you minimize the error, but that data is not representative of all the data. So you would overfit because in fact, it's over here. The best parameter is over here, but you overfit, so you go down here. The concept is you go down all the way to the bottom. Let's not do that. Let's stop early. Okay. So let me show you what this means. This is my error. I start with a high error. And I keep training. It's going to get down. 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 Maybe, you know, it can't get all the way to 0 because you don't have enough neuron. But if you have enough neuron, you will get down to 0. Okay. But that's not what you want. Okay. So by testing, maybe you get this now. Okay. That's the result I should give my client, right? Right. So I should give my client this result. But that's not good, right? So to be clever, what if I do my own pre-testing? I call it validation data set. And let's say it's another one. Can you see that? It's because I'm minimizing on this, but not on those. So this one is going to be bottom all the way, right? But maybe not this guy. Okay. So instead of training all the way to the bottom, reporting to this number, what I'm going to do is, so originally it was 80 and 20, right? Now I'm not going to do that. I'm going to do this. I'm going to do 70% and 20% and 10%. What I mean is this. Okay, let's I have a data set, and this is 100%. 100%. Okay. Let's draw it kind of horizontal. This is all my data. Okay. Yeah, all my data. This is the final out of sample data I'm going to hide. So 10%, let's say 10%. Yeah, that's 10%. Yeah, so 10%. Testing. This is the one that I should give to my client, how well it does. Okay, the model hasn't seen it. The model hasn't seen it. Okay, but if I use the 90% to train, it's going to go all the way down, right? So how about I have my own pre-testing. I call this thing 20% validation. And this thing is called 70% training. What should happen is, if I keep training, it's going to overfit. But because of this 20% validation, right? This is the point where I start to overfit. So I'm going to come back here. I'm going to come back here. However, this is still cheating. Why is it still cheating? Because I know when to come back. And I only know when to come back because I've seen this data set. So it's not fair for me to show this as my client's data because I'm cherry picking basically, right? So I have to show the performance with respect to another data set, which could be here. So that's my report. That's what I stop it with. This is, okay. Does that make sense? I'm doing hand drawing, I'm doing hand drawing. Okay. You, without stopping, you're going to keep running the model to the ground, basically, right? You're going to overfit the noise. In order to not overfit, you have to stop yourself. How do you stop yourself? You keep testing against another set of data. And at some point, first of all, it's going to go down together because the model is getting better. But at some point, when you start to overfit, you're going to do better on the data that the model trains. But the data the model hasn't trained, it's going to be fitting noise, right? Right? So at some point, the learning curve is going to diverge. It's going to diverge. That is the best place to stop. However, because you use that second data set to stop, you have seen it, okay? The model, the training algorithm hasn't seen it, but you have, okay? So think of a neural network as ANN 0, 1, 2, 3, all the iteration, right? It's keep training. You come back here because you know from the blue line that this is the best you can do. So then you report the red line. So you have to, so this is the 3 data set method. Does that make sense? Okay. Does that make sense? Okay, now, because you can say that all this thing is the machine learning step. There's a machine learning proper and there's a machine learning stopping, okay? For my textbook, if we have something like decision tree is not likely to overfit. So what I do then is, okay, let's put this thing as an optional topic. Okay, optional topic. So that's why in the textbook, there's training and there's testing, because that's an absolute must. Testing is an out of sample. Okay. Some neural network, you don't have to worry about overfitting. Some decision tree, you don't. Some neural network, you do, but okay. So that's why, okay, that's why what I'm going to do is, okay, now this is what you need to do. Procedure. Okay. Number 1, you prep the data. Number 2, okay, you basically, you build the model. Number 3, you report the outcome. Okay. Now, this prep the data has 2 steps, and we'll go to the notebook. One is to get in the right format and partition. Okay. You format the data so it's in XY form. Now, why is this? Well, you can imagine that you have data set. It's like a table. Okay. Client, characteristic, behavior, whatever, right? So these are all like numbers or attributes, okay? 20 of them. Depending on which thing you want to predict. Maybe you want to predict the 7th column using the first 5 columns and the last 3 columns, right? So you have to format it so that you don't feed the whole table. You have to say, what's the input? What's the output? That's basically what it means, right? So you format to input-output form, and you partition into test, training, and testing. Training and testing. Okay. That validation, that early stopping in is it's a very important thing that used all the time in a large model. But from your point of view, you just say, build me a model. And maybe you add an option and say, do some early stopping. So basically you give the model 90% data and it's going to separate out another 20% or something. Okay. So I can hide that detail from you for this class. So we'll call this training. Implicitly, there's early stopping in there or not, depending. So you format into, so what happened is you say, this is X1, X2 into Y. So basically you format into that. You partition, you build a model. You build a model. So you say something like model is equal to predict open data. Okay. And then you have something called evaluate model and data. Okay. You don't have to take a picture of this because it actually follows exact same thing as the book. Okay. Now, so let's see what it looks like from the textbook. From the okay. So first you partition, oh sorry, I stick it the other way around. You partition the test train. Okay. Now the easiest way to do this is use function called take drop. Okay. So let's try, we'll do this again, but type this with me. Okay. Your training data should be something like okay. So the way it should look is this. Okay. It should look like this. Okay. Basically, this is not real data. This is a number. So I have, okay, let's say I have 20 data point. Can you see that? 20 data point, right? 20 data point. I take the first 14 data point. I call it training set. So I'm doing 70-30. Okay. Doesn't have to be 80-20. It's this number are kind of like, there's no hard and fast rule. But for this example, I'm going to say I have 100% of data, which is 20 points. I take out 70%, which is 14 points as a training data. So if I take out 70%, what's my testing percent? 30%, right? So that's yeah, 30% off. Yeah. Right. Okay. So that's, so from X1 to X14, yeah, X1 to X14 is my training set. X15 to X20 is my test set. Okay. Now, my variable is Y. I always predict Y. My input is X. Now, in this case, what's the dimension of my input? 2, right? X1 and X2. So there's X1 of point number 1, X2 point number 2, X1 point number 2, X2 point number 2. So this is basically the format. The format is using an arrow. Now, I want you to do this. Minus, just type in the word minus. Minus, and then greater than, oops, sorry, greater than, and becomes an arrow, right? So basically, the data set is going to look like this. The data set is going to be a list of input and output. So for example, let's say input is 5 and 4 and 5, and output is 7. So that's one data point. Okay, that's one data point. Okay. Comma. What's the second data point? Let's say 2 and 3, and this becomes 9 or something like that. Okay. Right. That's the format. That's why the way I do it is table X. Okay. Now, next week, we'll actually work through the real data. So it won't be make up like this. So this is my X1, X2, X1, X2, Y, Y, right? Does that make sense? So let's say this is my data. Okay, this is my data set. So I call this my data. Okay. Training. Okay, so that will be how we do it. Now, let me see if I have a real example. K4, I'll come back to it. Okay. So now you type exactly like I do. Example data, machine learning. Kian. Yeah. Okay. Again, your term project should be based on your own data or example data. But let's say this is example data. Okay. Example data. Okay. Shift enter. There's a whole bunch of data set. Okay. Okay. Now, I'm going to give you for the exam something like this. These guys. The reason I will use this guy for your exam is because I use this in the book. Okay. Okay. So these two are in the books. So this one will be used in the exam. Okay. So example, machine learning, Boston Homes. Now these two problems, this one, I'm just going to describe. It is a prediction problem because the output Y is the price of home in Boston. Okay. So you input something like the size, the closeness to the street or whatever. Okay. And the prediction is Y is equal to value of the house. How much is that house worth? Fisher iris is a classification problem because iris is the name of the flower. And there are 3 species of flowers. So instead of apple, banana, orange, this would be iris type 1, iris type 2, and there are 3 types. Okay, so this will be the example I use in the book. Okay, the example, the data I would use in the exam will come from other things, obviously. Okay, now let's look at. I'm gonna take one. I take this guy again. I put example data. Now I know I use machine learning, so I said machine learning, comma Boston Home, and I add the word properties. This is to allow me to say what is in the data set. Basically, it's like looking at a spreadsheet without opening up the spreadsheet. Does that make any sense? When you work with a spreadsheet, how do you view the data? You open up the file, right? And you look at the heading, you look at the values, correct? Imagine in real life, that data has 1 million rows and 500 columns. Are you going to be able to visualize all of that by opening? You can't, right? So you have to do some kind of like what's called metadata information. How big is it? How large is it? How many items? Okay. Now properties is like say, okay, it's got data, description, dimension. So these are kind of like description of what the data looks like, right? Okay. Does that make sense? Now, why do I want to do this? Actually, this example is so small. It's so small. You can open up with an Excel, with a spreadsheet. I don't want you to do that because in real life, the data is not small. So you have to rely on, this is called like a heading or metadata information. Okay. So for example, if I would say something like example data, okay, and I put in something like dimensions. Yeah, let's put dimensions. Okay. The dimension is number of features 13, number of example 506. Basically, what this means is that it's got 506 row and 13 columns. Okay. Right. What else? How about description? Housing value in suburb of Boston. That's not going to go. Variable description. So now the 13 dimension, the first one is per capita income, per capita crime rate. The second number is proportional of residential land zone for, all kind of stuff. And finally, the last value is value. Okay, so the last one is a value. Okay, right. So these are kind of things. So I just make, okay, so basically 13 columns, right? Variable type, it's all numerical. Okay, so this is what the data looks like. It already comes in this format. Numerical, 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 nominal, numerical. Remember? Nominal, ordinal thing. Okay. The reason in Mathematica, numerical is for both nominal, is for both interval and ratio scale. And then nominal is for both nominal and ordinal. Just so you know, okay? And the output is numerical. So if I see this, what kind of problem is this? Prediction or classification? It's a prediction problem. I'm predicting prices. Okay. So now I'm going to separate data into train and test. Normally, let's say my data, okay? My data is equal to 1, 2, 3, 4, 5, 6, right? And if I do something like take drop, okay, say 4, 5, see? This is my full data, has got 6 points. I take the first 5, I make it one partition, I take the second 5. So this is one way of doing the train test partition, okay? So learn how to use take drop, but because of this problem, the training data and the test data is already partitioned, okay? And in fact, they partition into 338 home and 168, okay? Now, so this is data set number 1. So this is again, what's the output? Numerical, so it's a prediction problem. Second problem, this one is called classification. But how do you know this classification? Well, let's do this. Nominal, right? So if the output is nominal, it's definitely a classification problem. So, right. Now, we don't have time to go much into detail. I just want to show you one thing, that in Mathematica, building a machine learning model takes one line, literally, okay? Predictor. This is all I want to do, okay? So once again, okay, let me show you what the predictor, what predictor train looks like, okay? Now, predictor train is 360 homes. So this is 360 home. It has all this number, x1, x2, x3, x4, 5, 6, 7, 8, 9, 10, 11, 12, and predict price $21,000 or 21 something. I don't know. Yeah, let's say 21,000, I think. Is house price that cheap? Maybe this is an old example. Okay. Or 21 million. I don't know what it is. Okay. It's some unit I haven't looked up. Okay. So let's say it's an old apartment. Okay. $21,000 or $21 million. I don't know, whatever makes sense. Okay. So this is house number one, house number two, and how many houses? You got about 300 houses. Okay. So that's it. That's it. All you have to do is this: create a predictor. And there, it's done. This, you know, in say Python might take you half a page. This is one line. The function predict and data. Now, I just want you to look at this quickly. You go through this in your homework. In fact, the homework would be for you to replicate my steps, okay? But using other data set. So predictor function, the output is a function, and it's got some kind of data. Look, this is a description. Let me click this down. Number of training example, 338. Input type mix, right? So it's just not just numerical, it's also numerical and nominal and all that. Okay. What is the method? Anybody read it? Random forest, right? So for this problem, because it's not that complicated, Mathematica decided for you, I guess, as a sort of like a heuristic, maybe random forest works good enough. Okay, that's it. Okay, now if I did this and I say I want a special case, I want this one to be a, let's say, neural network, I can do that. Okay, what? Okay, so instead of saying build me a predictor, I specify method. Okay. Okay, follow me. Okay, predict, right? This will give you anything, comma, method. When you put method and you point to, and it gives you auto suggest. So it's got decision tree, gradient boosted tree, linear regression, nearest neighbor, neural network. So let's say I want to use decision tree. Okay. Well, sorry, let's make it neural network. Okay. That's it. Same thing as before. Okay. Training example. Okay, because it's a neural network, it takes a bit longer. In fact, if it's a neural network, I would probably do early stopping. Okay. Now, so it comes out, it takes a longer because maybe, you know, you specify neural network, it has a lot of parameters. It shouldn't take that long. I don't know why it's taking this long. Okay. So shift enter and, oh, there it is. It's doing it. Okay. Guys, see this? This is actually the learning curve. It's doing it live. Now, because this takes a while. Okay. So there, it's done. It is based on 338 sample mix, but it's a neural network. So now you have both models. Okay, so I built two models. One I specify the types, and the other one I don't specify. Okay, now the multi-label classification, same thing. Okay, except I'm using classifier. I'm not using predictor, right? So the word I use is classify. Okay. So if you want to make a mental note, the function you should use is take drop if the data is not separated already into train and test, and then classify or predict. Now, notice, okay, the first one I didn't specify. It decided logistic regression is good enough. Okay, and the classes, apple, banana, orange, it's actually Setosa, versicolor, and virginica. These are species. Same here, except if I say I want specifically decision tree, it's going to give specifically decision tree. Right? So this is basically it. Okay. Now, next week, when we come back, we'll say, well, now that we have built the model, how well is it doing? Okay. So that would be here, 3.2. Okay. Assessing machine learning performance. Now, this one is going to require a little bit of, well, not math, but yeah, a bit of math. You guys remember that when you did linear regression, you have this thing called R square? You guys remember that? Okay, those are like performance statistics, right? That's like telling you how accurate the linear regression model is. Okay. Likewise, in machine learning, there are performance statistics. Okay, but not all of them is R square. In fact, there's so many of them. Okay. Because this is a software, you can specify. There are like, if I remember right, there are about 20 or 30 statistics that tells you how good or no good your model is, beside R square. Some of them are intuitive, some of them are not. Some of them are more popular, some of them are not. Based on my experience, next week we'll go to the popular one. Does that make sense? Okay. So if you go to like a mathematical manual, it's going to give you all the options. That's fine, but it's not going to tell you which one are more popular. I will tell you which one are popular. Okay, and you can just assume that if I use it in the textbook, those are the popular one. Okay, those are the choice. Okay, now there will be different performance statistics for prediction as opposed to classification. Okay, but we'll see. It's not that difficult. Okay, I didn't manage time very well, so we don't have time for you to discuss the project. Let's I think next week should be okay. Okay, so next week, before we go to unsupervised learning, we're gonna go the performance aspect of supervised learning. Okay, in fact, after next week, if your project is about supervised learning or prediction classification problem, you can start your project next week. Okay, so you don't have to wait to all the editing. Okay, and in fact, I would say that even though graph data, yes, that's very interesting. Unsupervised learning, that's also very interesting. Chances are a lot of what you are going to be using in data analytics will be supervised learning, I would imagine. So next week would be a good time for you to start thinking for the last half an hour, or not start thinking, to think between here and the next class, what your project would look like based on some kind of machine learning data. Okay, so input, output, X to Y, supervised machine learning. Okay, if we discuss next week and it turns out that your problem is more amenable to unsupervised learning, like clustering analysis, we wouldn't talk about that. That's not a problem. Okay, but I switch supervised learning first because based on I guess, past experience, those tend to be something students are more interested in. Okay, just by sense. Okay, so next week, you should have already in mind, let's say, prediction or classification problem that you are thinking about. Now, that doesn't mean that that's all you're going to use, right? Because you have going to have visualization, you're going to have probability, statistics. So there's some element of that. Okay, so maybe your data would require you to do statistical fitting to find probability distribution. But then instead of going to the regression part, you want to use a bunch of variables to predict something. So in which case you are going to build a machine learning model, in particular supervised learning. Okay, and then you want to be comparing, well, maybe decision tree, maybe neural network, random forest. Okay, so that should be next week. Okay, yeah. So today, I think you probably don't have that much to turn in, but see what you can. Okay, turn in what you got. I'm going to hopefully let me give you one example as a homework. So when you get to exam part, you're not that scared. Back here, where's it? Example learning data. Okay, so the example, okay, there it is. Okay. What I want you to do is do this. Okay, this is also another trivial one I could have used as my book example. Titanic data. Okay, that's your homework. Okay, Titanic data. You need to do two things. Find out what data is all about. Again, you use this properties type thing, right? Decide whether or not this is a classification, a problem for classification, or, you know, prediction. Or should I just tell you? Well, okay, I'll just make life easy. I'll just tell you. Machine learning, Titanic, it's about the input is characteristic about the passenger, and the output is whether or not the person die. Okay, so if it's dead or alive, what kind of problem is it? Classification. Okay, so it's a classification problem. So I want you to, as a homework, take the machine learning data analytic class and follow the step. Okay, follow the step of classification. Okay, not a classification. The difficulty may be that depending on some data set, they may separate training and testing for you. Sometimes they don't. If they don't separate from you, you have to use take drop. And how do you do take drop? You determine how many data set, right? And you say calculate about 70%. Let's say 70%. So if I don't know, I don't remember the Titanic data. If Titanic data doesn't separate training and testing, I want you to do a 70%, 30% split. Okay? And follow through the rest of the example in the book. Again, these are all one-liners. You know, the earlier subsection, that's where you get, I do a lot of demonstration to show the concept. And that's what takes like a page of code just to make it look pretty. Okay. But the machine learning part, you can see it's only in one-liner. Okay. The thing that has like, you know, 20 lines that has to do with me dressing up the picture so it looks nice and stuff like that. That's not important. Okay. But this section here, this procedure, training and testing, you can do on your own. And that's what I want you to do. Okay. And I also want you to look at, okay, so this week is going to be a bit heavier than for homework. Part 1, do this. Part 2, go look at the video that I sent the link to. Okay. and explain to me what Gini impurity is. Okay, Gini, Gini, impurity. Okay, so that's 2 questions for your homework. Should we make it what, Friday? Friday, 5 o'clock, say? Okay. Yeah. You make a portal for them. So use my course view.